So we can take a few minutes and do take a couple of questions, but I also want to do 6-5 here. 6-5 is pretty short and pretty easy. So I probably need like 30 minutes or something to kind of do a decent job on that. And that's probably about it. Did you guys have questions from homeworks or anything that you wanted to talk about before we get rolling? If you don't, that's okay. I'll just start 6-5, and if you realize it, like, oh boy, yeah, I want to ask some stuff now, it's okay too. I get it. Mackenzie? 6.3, number 45. That's a shells problem, potentially, I guess. Okay. So here on 45, we're looking to use a cylindrical shell to find the volume of a sphere with radius r. So if I think about this as a picture, I know that a sphere is just going to be a circle that's rotated. And I'm going to center my circle at the origin and give it a radius of r. So the equation for that circle is going to be x squared plus y squared equals r squared. And if I rotate that about, it doesn't really matter the x or the y, because I'll end up with the same sphere, right? Do you have a preference? No. Okay. Let's rotate about the y then. So if I'm going to take a perpendicular cross section here to that, so this would be like, now Mr. Kulik is rusty on this. Okay. So this distance here is the height, or the radius, excuse me. And then this is the height, right? Everybody's okay there? I guess in this case, it probably wouldn't matter. So if I look at that, the height, or the r, is going to be the x-coordinate. So that's going to be plus or minus the square root of r squared minus y squared. And we can drop the plus or minus since we're talking about a distance. And the height is going to be the y-coordinate for that point, which again, plus or minus r squared minus x squared. But we're going to drop the plus or minus there. Now, what problem are you noticing we're running into right away here? Yeah, I have two different variables going on here, right? So what variable should I be integrating with respect to? If I'm rotating about the y-axis, y, okay. So let's leave this as just y, and we'll take this one as that. Is that wrong? Yeah, so you're right. Should be dx. So let's keep this as x, and we'll make this one that. So we have 2 pi, and then r is x, and then my height is r squared minus x squared. And we'll be integrating this from 0 to r. Everybody feel okay with that? Now, to do this integral, what are we going to have to use? U substitution. Yeah, what's the u in this case going to be? R squared minus x squared. So du dx is negative 2x. So du is going to be, yeah.
Is it r squared?
Yeah. Oh, yeah, but I mean,
Oh, it's a constant.
It's a constant. But yes, 100% should be r squared, yeah. So du over negative 2 is going to equal x dx. Everybody's okay with that? So let's go ahead and make our substitution. So 0 to r, and we have 2 pi, and then we have u to the 1/2, and we have times du over negative 2. And I'm just going to go ahead and do that. Okay. So let's do our antiderivative now. So the pi just is going to kind of get sucked out front, right? The antiderivative of u to the 1/2 is u to the 3 over 2 times 2 over 3. And then again, we're evaluating from 0 to r. And I don't like what's happening here. So we have negative 2/3 pi, and then we have r to the 3 over 2 minus 0. And that's not right. What's up? Oh, yes. Thank you, Mackenzie. Yeah. So we forgot to do that. Let's just do it now here before. So if I do u of 0, I get r squared, and u of r is equal to 0. So this should go from r squared to 0. So that's going to give me 2 pi r cubed over 3. Where'd I lose my factor at 2 somewhere, right? There should be 4/3 pi r cubed. We made some little mistake here somewhere, right? Where did it go? Who sees it? Mackenzie, do you see it? Oh, I see it. Go ahead. What were you going to say? No, that's okay. It's my initial setup is the issue. I should be integrating from negative r to r. So when I do that, we'll just put a 2 there and do our even function rule to make it from 0 to r. So there's my extra 2 there, my extra 2 there, and my extra 2 there. There we go. Does that feel okay, Mackenzie? Because really my radius should be this. Is all technically r, right? Not at all. What's the good news about shells and the AP exam? They're not on there. Now, if you take, again, you take a college calculus class, are they going to do shells? Heck yeah. Are they going to expect that you can do shells? Heck yeah. But in their infinite wisdom, the AP has decided that that's not part of what they're going to do. I don't know why. But just as a reminder, does that feel okay, Mackenzie? Yes. You're welcome. I picked that one because you had to do a U sub, because I want to find another one of these problems that where he snuck a U sub in it. You guys ready to talk about average value of a function? Is everybody, you okay, Mia? Mackenzie? It's okay? Okay. All right. So we know how to calculate an average, right? But if we want to talk about the average value of a function, we're talking about now having to add up infinitely many values for the function, right? When we start adding infinitely many things, what does that sound like? Sounds like an integral to me also. So blah, 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 blah. What this boils down to is the average value for a function. We can calculate by doing 1 over the bounds of, or the difference in bounds of integration times the integral from a to b f of x dx. So basically what we're doing is we're just taking we're finding area divided by width, and that gives you the average height for the function, which is the average value for a function, right? Everybody feels okay there? That's ostensibly the formula. Should look very much like an average formula, right? So let's do one. So find the average value of the function f of x equals 1 plus x squared on the interval from -1 to 2. So we just plug this into the formula. The antiderivative of 1 is x, and the antiderivative of x squared is x cubed over 3. So when we evaluate at 2, we get 2 plus 8/3. Minus, when we evaluate at -1, we have -1 plus negative 1/3. So that'll be 2 plus 1, that's 3. And then 8/3 plus 1/3 is 9/3, which is 3. So that's going to be 1/3 times 6, or just 2. Well, that's pretty doable, Mr. Kulik. That's no big deal. That's true. What if we wanted to instead find that number C that takes on that average value? Well, as long as our function is continuous, we're guaranteed that such a C exists. That's the mean value theorem for integrals. That's saying as long as f of x is continuous, then there's some value C on that interval that we're integrating over, where the function takes on the value of the average. So if we go back to the previous problem, and we want to know what that C is, well, we're just looking for the place where 1 plus x squared is equal to 2 on the interval from -1 to 2. So subtract 1 from both sides, square root both sides, we have plus or minus 1. And both of those would be okay, right? Because both of those are in -1, 2. So in that case, the C would be -1 or +1. So again, what are we really saying here? If we're looking for our values of C, it's just the place where we have the average value. So the way you can think about the average value is basically you're building a rectangle whose area is the same as the area under the curve. Right? That's all you're doing. And that's exactly what this is, right? This is the rectangle where the value of the function is the height and the difference in the endpoints is the width. And this is the area under the curve. So we did this already, right? I stole my thunder on this. I got excited. Right? Oops. So here it says, show that the average velocity of a car over the time interval t1 to t2 is the same as the average of its velocities during the trip. So that's saying that like average of its velocities would be like right? That's what the average of the velocities would be. the average velocity would be the integral from t1, well, oops, we need 1 over t2 minus t1, integral from t1 to t2 of s of t dt. I'm sorry, v of t, excuse me. Okay. What's the integral of velocity? It's position, right? The letter we used for position was S. Antiderivative. Yeah, that's, yep, thank you. Oh, you know what though, guys? The average velocity is just, you know, the total change in position over change in time. The average of its velocities is the average value for the velocity function. Excuse me. The right work, we just called things the wrong thing, which is a bummer. That's the idea, though, for this section. Isn't it a nice, easy topper to go on top of kind of a rough chapter in some regard? But that's nice, at least. So if you just look at the homework here, we have like 1 through 11 odd, 13 to 15, 17, and 26. Oh boy, it didn't go pop in where I wanted it to. If you look like 1 through 7 odd is just like plugging it into the formula, grinding an integral, should be pretty easy. 9 through 11, they're asking you to find the average value, so you're using the formula. Then find the C, the value for x that takes on that average value, and sketch the graph of f with the rectangle on there that has the same area as the area under the curve, which again, no big deal. 13 is kind of like a, it's like a mean value, or I'm sorry, mean value for integrals theorem problem. So if f is continuous and this derivative or this integral is equal to 8, show that blah, 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 blah. You're basically just using that mean value theorem for integrals to do that. 15 wants you to find the average value here on this integral, or for this function over this interval. And all they give you is a picture. How are you going to do that? Yeah, you're going to do the integral geometrically or by counting the boxes. Either one would be appropriate. And then you'll divide that by the distance or the length of the interval you're integrating over. That's it. No big deal, right? And then 17 and 26 are like some storyish problems. But aren't really, I don't think should be too big of a problem. What do you guys think? This is okay? This should feel pretty okay. All right. We got here right in time, right? So for the quiz here, again, I'll score this like as an AP thing. So, like 70% is going to be max credit or whatever for it. And then we'll work on down through there. I kind of give you like the 1, 2, 3, 4, 5 scoring guidelines, I think, on the paper. But I'm not sure what that'll even translate into, like out of 10. Like obviously 5 is 10, but I don't know if 4 is going to be a 9. Probably is going to be a 9. 3 will probably be an 8. So that like 1 is not 2 points. It's going to be like 6 points or whatever. That feels fair-ish. So you'll need probably, I would think 2 pieces of paper, because there's 2 parts. It's okay to be scared, guys. It's not a big deal.
We can still grab the notes.
Yeah. So as a reminder here that one of these is calculator, the other is no calculator. I'm going to give you guys the calculator section first. After you do that, you can turn it in, and I'll give you the no calculator section afterwards. And you can feel free to write all over this guy. That's no big deal. And again, like, remember that like 50% is like 4 territory. So if you feel like, yeah, I might have done half of that right, that's pretty good. That's okay. So this is what you're looking at are like previous AP exam free response question that pertains almost exclusively to these areas under curves and volumes of rotation that we've been working on.